And this is not so bad. This should really remind you of last week when we were graphing polynomials on Monday. But unlike when we were graphing polynomials and graphing quadratic functions, it's not going to be enough to just generate a table of values. I'll show you an example. If I tried to just graph this by generating a table of values, then you'll see what's going to happen here. I would start by making up some x values and determining what is y if my function I'm trying to graph is y equals 1 divided by x. And x is 1, then y is just 1 divided by 1. And if x is 2, then y is 1 divided by 2. And if x is 3, y is 1 divided by 3, and so on. And for this function, it's pretty easy to fill out the table. Like 1 divided by negative 1 is negative 1. 1 divided by negative 2 is negative half, and 1 divided by negative 3 is negative 1/3. What happens when x is equal to 0? Y would be 1 divided by 0, but we can't divide by 0. And so right here, we say that the function is undefined, because 1 divided by 0 is not a number. And then whenever I went here to graph my function using my table of values, I'd say, here is the point where x is 1 and y is 1, and x is 2 and y is 1/2, and x is 3 and y is 1/3, and then 1/4, and then 1/5, and 1/6, 1/7, 1/8, 1/9, and 1/10. Over on the other side, here is where x is negative 1 and y is negative 1, where x is negative 2 and y is negative 1/2, where x is negative 3 and y is negative 1/3, and negative 4th, and negative 5th, and negative 6th, and negative 7th, and negative 8th, and negative 9th, and negative 10th. And then to graph using a table of values, I just have to connect these dots that I placed. But I'm here to tell you that this is a terrible graph of what I'm trying to graph, right? Like the function y equals 1 over x doesn't really look very much like this. And again, my point is that, normally with polynomials or quadratic functions or whatever, especially lines, making a table of values and then connecting the dots is almost always good enough. But in this case, it's really not. I'll show you what y equals 1 over x is supposed to look like. And if we had graphed this correctly, 1 over x is supposed to look like this. And the part that we missed out on when we graphed it a moment ago is the part in the middle where it looks spiky. Because we got the part where it goes up to 1 comma 1, right? X is 1 and y is 1. But then all of this stuff is not really represented well in my table of values. And the reason it shoots up like this is because whenever my x gets to be a really small number that's really close to 0, then 1 divided by a really small number is a big number. Like 1 divided by 1,000th is 1,000. That's a big number, right? So that's why it shoots up on either side. If I then plot a function that's a little bit more interesting, we can see this again. Like, what if my denominator is something like this? Then what I say is every root in the denominator, like x equals positive 3, x equals positive 1 and x equals negative 2, those roots in the denominator lead to these spiky vertical parts of the graph that we call poles.
Are they also called asymptotes?
Yeah. So some textbook authors might call this a vertical asymptote, depending on the book you're reading. And
Aren't the roots the ones that cross the x-axis?
great question. So in this function, y equals 1 over all of this junk, there's actually no x-intercepts. Because an x-intercept would be a place where y is equal to 0. But if you set y equal to 0, 0 equals 1 over a bunch of stuff, you don't ever get x value that gives you a y value of 0. So this time, x equals negative 2, for example, we're talking about plugging in a number right here, where if I have a value very close to negative 2, and I get something very close to negative 2 plus 2, that's something very close to 0 again, right? And then I don't care what I'm multiplying by as my other factors in the denominator, right? Because if this is very, very close to 0, then the whole denominator is going to be a very little tiny number. And 1 divided by a tiny number makes a huge number. And that's why it shoots off to infinity on either side. So for my notes and for all our practical purposes in class, I call these poles, but again, you might call these vertical asymptotes. But basically, it's a vertical line, and we're going to draw these as dashed lines on the paper, where our curve for our function is not going to cross over this line. It's either going to go up to positive infinity or down to negative infinity on either side. And this is what it looks like. Now, to better answer your question, you said, aren't the roots the places where you have x-intercepts? And that is true for roots in the numerator, right? So let me put down some roots in my numerator. Now, in the numerator, one of my roots is x equals negative 1, and that is an x-intercept. Another root in my numerator is x equals positive 2, and that gets to be an x-intercept. Roots in the numerator give you an x-intercept. Roots in the denominator give you a pole. Good question. Okay. When we talk about end behavior, we graphed polynomials last Monday, and we said end behavior for a polynomial was like, down on the left, up on the right, or something like that. End behavior for polynomials was pretty basic. For rational functions, it depends on whether your rational function is proper or improper. If you've got a proper rational function, remember that means the degree of the numerator is less than the degree of the denominator. In that case, the end behavior approaches y equals 0. That's a horizontal line. Or, the same thing is you could say the end behavior approaches the x-axis as you go off to the left side and go off to the right side. If you instead have an improper rational function, for an improper rational function, we can do polynomial long division. And whenever we do polynomial long division, we're going to see that the end behaviors approach the quotient. And I'm talking about the quotient you get from long division. And so maybe your quotient polynomial is a line, or maybe it's a parabola or something else. And as you go off to the left and go off to the right, your rational function is going to get closer and closer to whatever that line or parabola looks like. We'll see some examples here in a minute. But first, in case you're wondering, why does an improper rational function eventually approach the quotient? It's because long division allows us to rewrite our improper rational function as a mixed form where we get the quotient plus the remainder over the denominator. And here's a little example of just what that might look like. You might have something like 2x minus 3 plus, I don't know, 11x plus 5 over x squared plus 1. Right? Just a little example to work with. And so here is an improper rational function that I wrote down in mixed form. And what I want to draw your attention to is, what if I took this last part, not the quotient, this would be the quotient right here, but this last part that's remainder over denominator, and I multiply this times 1 over x squared in the numerator, and I multiply by 1 over x squared in the denominator. Remember, that's like multiplying by 1. I haven't changed the value of anything. I'm just writing the same thing in a different way. Well, the 2x minus 3 gets to, hang out by itself for a little while. And then now, this part is going to become 11 divided by x. And 5 divided by x squared. Divided by, x squared divided by x squared is just 1 plus 1 over x squared. And what we were asking is, what about my end behavior? Well, end behavior, whenever I say we're going to go off to the right or go off to the left, what I'm saying is, what happens when x becomes a really large number? What happens when the absolute value of x is approaching positive infinity, or what happens when x is approaching negative infinity? What happens when x is getting really, really, really big? So, imagine just the biggest number you can think of, right? X equals 1,000. Then 11 divided by 1,000, that's a really, really small number. In fact, it's so small that when I'm graphing this, I can ignore it. What about 5 divided by 1,000 squared? That's 5 divided by a million. That's a really small number, and I can ignore it. 1 is fine. That's just a 1. What about 1 divided by a million again? Well, 1 divided by a million, that's a really small number. Small enough where I can safely ignore it. And it only gets smaller as x gets bigger. So basically what I have is 2x minus 3 plus something that's practically 0 divided by 1. And that's why we only care about the quotient if I'm asking you about the end behavior. The other stuff does matter in the middle of the function where there's still stuff happening. But whenever I talk about the end behavior, I say let's go far enough to the left or far enough to the right. We only really care about the quotient. Now, this is what you grabbed when you walked in. It was notes, and it's got a 5-step process for graphing a rational function. Step number 1, we find the y-intercept. That's super easy. You just plug in x equals 0, and you simplify. Step number 2, the end behavior is going to be determined by whether you've got a proper or improper rational function. If you've got a proper rational function, then think about this. It's kind of like your quotient is 0. And so if we say the end behavior approaches the quotient, well then in this case, for a proper rational function, we're going to approach the line at y equals 0. On the other hand, if it's improper, our end behavior approaches the quotient like we talked about. Step number 3, we're going to factor this, and we're going to cancel out any common factors. Step number 4 says the x-intercepts are the roots in the numerator. And just like we talked about last Monday, the multiplicity rules work exactly the same. So odd multiplicity for a root in the numerator means your curve's going to pass through the x-axis. But an even multiplicity means you're going to hit the x-axis and you're going to bounce off. That works just the same. What's new here for rational functions is step number 5. And we're going to be able to find the poles by looking at the roots of the denominator. And there are multiplicity rules for this. I'll draw a little picture here. If I had a pole with an odd multiplicity, it might look like this. Okay? In other words, on one side, I might be going up to positive infinity, and on the other side, it looks like I'm going down towards negative infinity. That's what an odd multiplicity looks like. On the other hand, if I have a pole that has an even multiplicity, it's going to look like this, where on either left and right side of the pole, we're kind of going in the same direction. In fact, I don't even know why I'm drawing this. I could just show you. Everything we've seen so far on Desmos has been poles like this that have odd multiplicity. Remember, a multiplicity of 1 is odd. But now what if I look at the pole that happens at x equals positive 3, so the one on the right, and then I'm going to change that from a multiplicity 1 to a multiplicity of 2. So it's still there, but the difference is that it doesn't switch from positive to negative. It just stays positive to positive. Another way you might see this is, like in this function here in purple, now this pole at x equals positive 3 has an even multiplicity because of this number 2 here. But you can tell it doesn't change sides, it just goes from negative to negative. So odd multiplicities switch sides and negative, or even multiplicities don't. And then we'll get ready to draw it, and I'll show you how that works. I have a whole bunch of examples today because I think this is a little bit of a tricky topic. It's a tricky skill to learn. And so I'm going to show you a bunch of examples today in class. At any point, raise your hand and let me know if I did something confusing, and we'll discuss what's going on. But I figure the more examples I show you, the better feel you'll get. Okay, step number 1. Let's find the y-intercept. To find the y-intercept, I set x equal to 0, plug that in, and simplify, and then tell me what I get for y. This is going to be positive 4/3. Because negative 2 times negative 2 is 4. And so 4/3 is going to be right here. It's like 1 plus 1/3. There's my y-intercept. That was pretty easy. Step number 2 is saying, I want to know about my end behavior. Now, for my end behavior, is this a proper or improper rational function? This is improper because this is improper anytime the degree of the numerator is greater than or equal to the degree of the denominator. So don't forget about that, or equal to. Because in this case, the degree of both is 1, and that's what makes it improper. Okay, so it's improper. And then in order to do long division to this, I first have to rewrite this thing in expanded form. That's what it looks like in expanded form. And then here's my long division step, where I'm trying to find the quotient. Remember? And in fact, I really don't care what the remainder is. I only care about the quotient. And so maybe we can even stop early if we're careful about it. The first question I ask is what times x gives me negative 2x? Negative 2. And so I multiply negative 2 times x is negative 2x, and negative 2 times 3 is negative 6. And you can put down some parentheses and you subtract. 4 minus negative 6 is 10. And I can stop, right? Because the degree of my remainder is less than the degree of my denominator. And in fact, I don't even really care about the remainder part. I only care about the quotient when I determine my end behavior anyways. And so my quotient is negative 2, and that tells me my end behavior approaches the line at y equals negative 2. So here is the horizontal line, y equals negative 2. And we're ready to move on to step number 3. And step number 3 says I want to factor this, right? But it's already factored. That's good. Step number 4 says, what about my x-intercepts? Where are those? So you got to remember, the x-intercepts, those are the roots in the numerator.
All of the one in the denominator are the asymptotes.
Exactly. So in the numerator, I only have one root. It's at positive 2. And the corresponding multiplicity is 1. Because if you don't see an exponent, that means the multiplicity is 1. And then step number 5 says, what about my poles? Those are the roots in the denominator, and you're right, that's negative 3. And the corresponding multiplicity is 1. Now we're ready to graph. And this is how it looks to graph. I'm going to put a vertical dotted line here where my pole is at x equals negative 3. And then I'm also going to put a dot where my x-intercept is at positive 2. And then I'm going to start by putting my pencil down on top of my y-intercept, and I'm going to move to the right. And as I'm going to the right, I'm going to try to connect the dot where that x-intercept is. And then right there, should I go through the axis or should I bounce off of the axis? The multiplicity is 1 at that x-intercept, and 1 is an odd number, and so I'm going to cross the axis. So here I am, I'm going to cross the axis, and then as I continue to go to the right, my end behavior is that I approach and get closer and closer to this flat line, just like that. Now I start by putting my pencil down on the y-intercept, and I move to the left. And as I'm moving to the left, I'm approaching this pole, and I can't just draw the line through the pole. I have to either go up or down. This time, I have to go up. I don't have a choice. Because if I tried to turn this curve around, and I tried to go down as I approach the pole, the issue is I don't have an x-intercept, and I can't cross the x-axis unless I have a little x-intercept there. And since I cannot cross the x-axis, that means I've got to go up. This pole has a multiplicity of 1, and 1 is an odd number, and that tells me that I have to show up over here on the opposite side. And as I continue to go to the left, now I'm thinking about my end behavior, which is going to get closer and closer and closer to this flat line right there. So right there in purple, that's my best attempt at drawing this rational function. And it might not be perfectly precise, but what I care about in this class is I want to get the y-intercept correct. I want to get the x-intercepts correct in their multiplicities. I want to get the end behavior correct, and I want to get the poles and their multiplicities correct. If you've got those 4 things, 100%. That's all I care about. Any questions so far?
So one of the multiplicities is for the x-axis and the other is for the y-axis?
In step number 4, we find the x-intercepts by looking at the roots in the numerator. And the roots in the numerator have a multiplicity that tells you whether or not you go through the axis if it's odd, or bounce off the axis if it's even. In step number 5, we locate the poles by looking at the roots in the denominator. And the roots in the denominator also have some kind of multiplicity. If their multiplicity is odd, it tells you that that pole is going to be opposite signs on either side of the pole. It might be like negative on the left side and positive on the right side, or positive on the left side, negative on the right side, but it switches. And if the multiplicity of a pole is even, then it doesn't switch. This is the picture I showed when I said this the first time, but
Sorry.
it's okay. I understand. It's after lunch. Everybody's sleepy. I totally get it if you, doze off or miss something. No worries. But right here on the screen, you can see 3 poles. The first 2 on the left have odd multiplicity. And you see how they switch from negative to positive whenever you go from one side to the other?
Yeah. Okay.
But the last one on the right, that has an even multiplicity. You see the exponent 2? And if it has an even multiplicity, then it doesn't switch. Just like, here's an x-intercept at x equals -1. If I make that have even multiplicity, then now it doesn't pass through the axis, it just bounces off. That rule is the same as for graphing polynomials. That's the new thing, I guess, is learning the multiplicity rules for poles, how those look different. But again, it's okay if you're still catching on, because we'll have lots more examples. And maybe before we move on, we can check our work really quick. So here's how we check our work. I'm going to plug in the original function into Desmos, which is going to be y equals -2 times x minus 2 over x plus 3. Yep. And let's see if we did this correct. So I said there was a pole at x equals -3. And I said my end behavior approached the line y equals -2. And that looks pretty much exactly how I drew my curve on my notes here. And you can double check the x-intercept should be at +2. And there it is. You can see the x-intercept's at +2. And so checking your work on Desmos is super duper easy. You should always do that before you move on to the next one. All right. Moving on to the next one. This one is admittedly a little bit tricky, and I'll tell you about the tricky part whenever we get there. First of all, step number 1 says I want to find my y-intercept. And my y-intercept occurs when x is equal to 0, and we plug that in to find 3 times 0 minus 9 over 0 squared minus 5 times 0. So my y-intercept is -9 divided by 0.
Undefined.
It's undefined. Perfect. That means I do not have a y-intercept this time. I don't have a y-intercept. there's not a place where this curve is actually going to pass through the y-axis. Step number 2, we move on and we say, okay, what about my end behavior? Is this a proper or improper rational function? This is proper because the degree of my numerator is 1 and the degree of my denominator is 2. And that means my end behavior approaches the horizontal line at y equals 0. Or if you want to think about it like this, it approaches the x-axis. That's always the case for a proper rational function. Okay, step number 3 tells me that I want to factor this thing. And the numerator factors as 3 times x minus 3. And the denominator factors as x times x minus 5. Step number 4 tells me, let's make a list of our x-intercepts, which are at just positive 3, right? That's just the root in the numerator only. And the multiplicity, since I don't see any exponent here, is just 1. And I know I'm going to cross the x-axis there. Then step number 5 says, let me make a list of my poles. And the poles occur at 0 and 5. And the multiplicity of each one is just 1, because again, I don't see any exponents. And so I have everything I need to graph. And I might start by putting a dot down where my x-intercept is. Here's my x equals positive 3 x-intercept. And I'm going to put a horizontal dotted line where my end behavior is. But remember, my end behavior is just the x-axis. And then I'm also going to put 2 vertical lines here for my 2 poles. And the fact that the y-axis is a pole tells you why I don't have a y-intercept. And then also there's one at x equals 5. I'm putting this down. Okay, this is the tricky part. Normally, I would like to start by putting my pencil down on the y-intercept and then drawing as I go to the right. But the crappy part here is that I don't have a y-intercept. And so this time, and this is a special case when you don't have a y-intercept, but we need at least one more point. In order to graph this thing. It doesn't matter which one you choose, but I like the idea of choosing x equals 1 in this case because I think it will be easy to calculate. So we plug in x equals 1 and we're going to calculate the y value that we get. And that gives me y equals 3 minus 9. So it's 3 times 1 minus 9. Divided by 1 squared minus 5 times 1. And the numerator is negative 6. The denominator is negative 4. And this is together positive 1.5. So when x is equal to 1, y is equal to positive 1.5. And I'm going to plot that right here. X is 1, y is positive 1.5. And this is where I'm going to start from now, since I don't have a y-intercept. So let me put my pencil down here, and I'm going to move to the right. As I'm moving to the right, I connect the dots, and then I think, okay, now that I'm here, should I cross the axis or should I bounce off? I cross the axis, because that x-intercept has an odd multiplicity. And then I keep going. As I approach this pole, I have to go up or down. I can't cross it. And this time I have to go down because I can't go up. There's not another x-intercept, so I can't go back up here. Now this pole at x equals 5 has an odd multiplicity, and so I have to restart on the opposite end. And as I go farther to the right, I make my curve get closer and closer to the end behavior, and the end behavior is approaching the x-axis, like that. Okay, now we restart right here, and I move to the left. As I move to the left, I'm approaching another pole, and this time I have to go up because I can't go back down. I don't have an x-intercept, so I can't cross the x-axis, so I have to go up. Once again, the pole at x equals 0 has an odd multiplicity, and if it has an odd multiplicity, then we restart at the other end, and we keep drawing to the left, and as I continue to draw to the left, I'm going to try to make my curve get closer and closer to the end behavior, which is the x-axis. Just like that. And again, it's not going to be perfect, but at least I know I got, well, there wasn't a y-intercept. I got that right. I got the x-intercepts right, I got the poles right, I got the multiplicities right, I got the end behavior correct. And all those things are the only things we care about, so this is good enough. We can always check our work, so let's take a look at 3x minus 9. Divided by x squared minus 5x. And this is how it should look. My poles were at x equals 0 and x equals 5. And my end behavior was the x-axis. And that looks exactly like what I got, so I don't have to worry about that. It seems good. The only x-intercept is at x equals 3, and we cross the axis there, and it checks out. Any questions about that example? All right, we'll keep going. So once again, graph the following rational function. Step number 1, let's find my y-intercept. I plug in x equals 0, and my y-intercept is negative 3 divided by negative 1, which is 3. The y-intercept is the easy part. Now let's talk about the end behavior. Is this a proper or improper rational function? Improper. Because the degree of the numerator is greater than or equal to the degree of the denominator. And if it's improper, then we have to do long division. And I say, what times x gives me x squared? X. X times x gives me x squared. X times negative 1 gives me negative 1x. And then I put down parentheses and I subtract. And then negative 2 minus negative 1x is negative 1x. Bring down the negative 3. And now I ask, what times x gives me negative 1x? Negative 1. And so negative 1 times x gives me negative 1x. Negative 1 times negative 1 gives me plus 1. Put down my parentheses and I subtract. Negative 3 minus 1 is negative 4. And I can stop. Because you're allowed to stop when the degree of your remainder is less than the degree of your denominator. In this case, 0 is less than 4. And I don't care about the remainder part. I only care about the quotient. And that tells me my end behavior approaches the line y equals x minus 1. Y equals x minus 1, that's a line that has a slope of positive 1 and a y-intercept of negative 1. And so here I am, I'm drawing my end behavior line. That positive 1 slope, just like that. The next step, in step number 3, says I need to factor this. So if I were to rewrite this in factored form, the numerator would factor as, very good, x minus 3 and x plus 1. There's no factors in common that I can cancel. But looking at the factored form, I can tell where my two x-intercepts are. Those would be at 3 and negative 1. The multiplicities are once again pretty boring. It's multiplicity 1. If I look at the denominator in this factored form, then I can tell where my pole is. There's only one of them at positive 1. And again, the multiplicity is still boring this time. It's not always like that, but sometimes you only get ones. Now, I'm ready to draw, but I have to put a vertical line where my pole is. So here's my little pole, or you can call it a vertical asymptote if you want, at x equals positive 1. And I'm going to put another dot down where my x-intercepts are. Here's positive 3, and here's negative 1. And let's start by putting my pencil down at the y-intercept. And as I move to the right, I'm immediately faced with a pole, so I have to go up. I can't go down because I can't go through the x-axis if I don't have an x-intercept. And then since this pole has a multiplicity of 1, that's odd, and I have to start from the other end of the pole and go like this. I reach this x-intercept, and should I cross the axis or bounce off? Cross. Because, again, this x-intercept has a multiplicity of 1, and 1 is odd. If it's odd multiplicity, then we cross the axis. As I go to the right, I'm approaching my end behavior, and this time my end behavior is the line y equals x minus 1. So that's the end behavior. On the left side, let's put our pencil down again on the y-intercept. And then I'm going to start to draw in the left direction. So I connect this dot. This x-intercept has a multiplicity of 1. And since 1 is an odd number multiplicity, I go through the axis. And as I draw off to the left, I'm once again going to approach my end behavior line, which is just like that. So this time, in green, you can see my best attempt at graphing this rational function x squared minus 2x minus 3. Over x minus 1. And it has a pole at x equals 1. And I said my end behavior was y equals x minus 1. And that's how you check your answer on Desmos. Everything looks like it checks out pretty well. Any questions about this one? All right. So, step number 1 in a new example is we find the y-intercept. We can find the y-intercept by setting x equal to 0. And if x is equal to 0, then y is equal to 8 divided by negative 6, which is negative 4/3. It's like negative 1 minus 1/3 right here. Step number 2, we need to determine the end behavior. Is this proper or improper? Improper. If it's equal to, then it's improper. And if it's improper, then I have to do long division. And so this is me doing long division. And I ask the question, what times x squared gives me 2x squared? 2. And whenever I multiply and I subtract and whatever, I'm going to get my remainder. But remember, I don't care about my remainder. I'm only trying to figure out the end behavior, and the end behavior is the quotient. And this is my quotient. So my end behavior approaches the line y equals 2. And I don't have to do any more long division. All right, step number 3, I need to factor this. And so let's rewrite this thing in factored form. The numerator has the number 2 as the greatest common factor, so I went ahead and took the 2 out. And then the rest of the numerator factors as, yep, x plus 2 times x plus 2. I'll just go ahead and write x plus 2 squared. And the denominator factors as, perfect. Okay, and looking at the factored form, I can tell that I have one x-intercept that occurs at negative 2. And what's the multiplicity now? 2. I've got 2 poles at 2 and negative 3, and the multiplicity of each one is 1. All right, so y-intercept is negative 4/3. I put that down there in green. So I'll put my x-intercepts. There's only one of them. I'll put it down in green.
So the x-intercept doesn't get affected even if it's squared?
No. No, it's just the root in the numerator. The root in the numerator is negative 2. It will have a different behavior, right? The curve is not going to pass through the axis now, because now the multiplicity is even, and you just bounce off the axis. So we will see that. So I've got my x-intercept, I got my y-intercept, I got my end behavior. Let's put down the 2 poles. And so there's a pole here at 2 and negative 3. Putting my dashed lines now where the poles go. And here I am. I'm going to try to graph this thing. I'm going to put my pencil down on the y-intercept, and as I move to the right, I have to go down as I approach the pole. Since this pole has a multiplicity of an odd number 1, I switch and go up from the other side. And then as I go off to the right, I approach the end behavior at y equals 2. Now I restart at the y-intercept. This time I go to the left, and I have to connect the dots. And should I bounce or cross the axis here? Bounce. Because that x-intercept has a multiplicity of 2, and 2 is an even number. Then I approach the pole, and the only direction to go is down. And this pole has a multiplicity of 1, and 1 is an odd number, so I show up on the other side here, and it flattens out towards the end behavior as I go off to the left. It says, write the rational function in expanded form that generated the graph shown, and here's what you would do. We're going to make a list of my x-intercepts. And their multiplicities. And we're going to make a list of my poles and their multiplicities. And then we're going to write this thing in factored form first. I know that the question says expanded form, but we're going to write it in factored form, and then we expand it, okay? Now, I've got two x-intercepts. What are they? -2, okay. If I give you a hint that says all multiplicities are either 1 or 2, and you see the curve crossing the axis, that means these multiplicities are 1. Because if they were multiplicity 2, then they would be bouncing off of the axis. They wouldn't be crossing. Okay, I've got one pole. Where is it? -1, and the multiplicity is 1. If it had multiplicity 2, then it would look like a TP or a well, but since it goes in any direction, it's multiplicity 1 because that's odd. Okay, now if I have that, I'm ready to write down my factored form, and my factored form is going to look like y equals some leading coefficient times x minus 1 times x plus 2 divided by x plus 1.
Does the y-intercept on
It will. So right now, I just made sure that I get exactly the right x-intercepts, because those are the roots in the numerator. And I got the right pole, because that's the root in the denominator. Now, you're right, I should care about my y-intercept. And the y-intercept, that's the trick to figuring out what my leading coefficient is, right? I need to know what that a is. Well, let's look at the y-intercept. And the y-intercept says that when x is equal to 0, y is equal to -2. So here's y equals -2. And if I replace x with 0, this is the equation that I get. And that tells me that a is equal to
0?
1, right? Divide both sides of the equation by -2, and -2 divided by -2 is 1. And if a is 1, then we don't have to write it. Maybe that's not the case, and maybe a is some other number, like 3 or -5. But in this case, a was just 1. And when I go to write my expanded form, now I just have to expand the numerator. And the denominator is still just x plus 1. And that is how you answer that kind of question. Take a little pause so you can catch up in your notes. And to recap, we said make a list of the x-intercepts, make a list of the poles, check the multiplicities based on whether it bounces and whatnot. Then write down the factored form. Don't forget you might have some leading coefficient, and then the x-intercepts are the roots of the numerator, the poles are the roots in the denominator. You can solve for your leading coefficient by using the coordinates of your y-intercept, and then you can expand the same way we've always expanded. One more example just like that, and then we call it a day. It says, write the rational function in expanded form once again. That generated this graph. And so using the same procedure, let me make a list of my x-intercepts and their multiplicities, and a list of the poles and their multiplicities. And then we write it in factored form. Where is my x-intercept? There's one of them.
0.
It's actually right here.
Oh.
Yeah.
That was tricky.
It's -1. And the multiplicity is 1, because clearly it's odd if it passes through the axis, and the only odd number it could be is 1, according to my hint. And then the two poles happen at 4 and -3, and those multiplicities are also odd because they switch from negative to positive. And then the factored form must be y equals some leading coefficient times x plus 1 in the numerator, and in the denominator, x minus 4 times x plus 3. To solve for the leading coefficient, I need my y-intercept. But my hint this time says that my y-intercept is 0, -12. I provided that in the hint because it's hard to see where that is exactly. And so if I plug in y equals -1/12 and x equals 0, I get this, and that tells me that a is equal to 1, and that means, -1/12 divided by -12 is just 1. And again, this is not always the case. It was just coincidence that it happened in my examples. But if a is 1, I don't have to worry about it. Writing this out in expanded form, well, my numerator can stay x plus 1, and then my denominator gets to be x squared minus x minus 12 when I expand.